only if you have watched thermodynamics, because then you have to also do the worksheet, right? So
Yeah.
so
So I'll catch up with it.
yeah, you can skip the class, but for others, if you want, I can also take it 2 p.m. It's fine. 2 p.m. Pakistan time. You
So
guys
2
can.
p.m. is
It's
fine.
good to understand.
That's better.
2 is fine because you guys have holiday, right? And then you can wake up by 12. I believe most of the people
Yes.
can wake up by 12. Okay, fine. 2 p.m. Pakistan time.
2 p.m. on Saturday?
2 p.m. on Saturday, yes. But the thing is,
Okay.
who will take the responsibility to remind me? Because I am the biggest,
So that's great.
I forget
So,
things.
sir, Saturday we will be done by 3, right? Because I have see it by at 3.
You have bio at 3?
Yes, sir, on Saturday.
You have bio at 3, so fine, you can take physics at 2. Wouldn't be comfortable for you?
No, bio is on 5 p.m. PST, and this is at 2 p.m. PST. No, it's 3 p.m. KST. So that this one would be 12 KST.
Right.
Yes,
Okay, sir, my bad.
it will be 12 KSA. Thank God. Okay. Finally, our differences have, resolved. So now we can move on.
So can you clear it out for me as well? What time it is?
2 p.m. Pakistan time. I'm writing it.
Okay.
2 p.m. PK time.
Same.
And Gatika will text me on WhatsApp to remind me. Okay? 2 p.m. Pakistan time. Saturday.
Okay, sir, I will do.
Okay, now. Fine. So yesterday we did this, and today we are going forward with electric fields, and this time let's just start off with the Coulomb's law. Now this is where the real A2 starts. This is called Coulomb's law, and this is very simple because it actually reminds you of gravitational Newton's law of gravitation. Like, I'll write it and you'll see. So Coulomb's law states that the force of attraction or repulsion between two charges is directly proportional to the product of their charge and inversely proportional to the square of distance between their centers. So basically it is the same thing. So for the very first mark, you guys need to remember the force of attraction is directly proportional to the product of charge. So this is 1 mark. And the second mark is when you write an inversely proportional to the distance between square of the distance between the centers. Okay. Okay. Now, so basically what it means is that there is this charge. Say, okay, let me make a bigger charge because we can. Q1, and this is another charge, Q2. This is their centers. So from center to center, this is their distance r. The basically above relationship states that the force is directly proportional to the product of their charge, and force is inversely proportional to the square of distance between their centers. Now when you combine this, you're gonna get F equals to F proportional to q1 q2 over r square. Generally you would also find some people writing it as capital Q small q over r square. That is just to differentiate, them. It is the same thing. Anyway, so when you put a constant here, the constant is k, and k is not a real constant. K itself depends on basically, well, let me write what is k first. So k is the electrostatic constant, and the value of k is 8.99 times 10 raised to power 9 Newton meter square second, coulombs minus 2. So basically this is only the value is required. It will also be given there, but k itself is basically derived from 4 pi epsilon. It's basically the Greek e and this. Here I would like to tell you that this epsilon is called the permittivity of free space. And the permittivity of free space basically means it is a value of 8.85 times 10 raised to power minus 12 meter minus cube kg minus 1 second 4 ampere 2. You don't need to remember the units of the value. You can always look at from the whole thing, but you just need to remember the formula for k. Now I just want to tell you that basically permittivity of free space means just vacuum, because electric field can get affected by the charges within air or any other material. So which means that it is the value that represents how permissible it is for the electric field to be produced or reproduced in a vacuum. So there could be other permittivities as well, but in our course usually you'll see permittivity of free space. So just these two values are required. So right,
can you repeat what is permittivity?
It's basically in a vacuum how easy it is for an electric field to be produced. Do you understand?
Yes, sir.
So in a different material like air, water, metal, whatever, it would be a different value. But we only look at the vacuum right now. Okay, unless they've stated it. Okay, now. So right now, for the force, I'm going to write two formulas. Generally, I would love to remember, because it is easier to remember, that is k q1 q2 over r square. Or you can remember it as 1 upon 4 pi epsilon times q1 q2 over r square. Both are the same. Or if you would like to remember it as k q over r square, that is also fine, because you just need to separate them. Anyway, the next thing you guys need to understand is you need to learn about the derivation of electric field strength, and this derivation is included. It might also come in your exam. Usually it comes for like 2 marks, so it's pretty easy. So right now we have learned previously that electric field strength is given by force per unit charge. So that's the first part, and the second part we've learned is F is equal to K Q over R square. Is it clear, everybody? Now what I'm going to do is I'm going to replace this F right here, and if I do that, E is going to be equal to K Q over R square divided by Q, like this, which basically helps us cancel out one of the charge, and then we only have E is equal to K Q over R square. So this is the formula that you guys need to remember. Is it clear, everybody? So either this formula, or you can expand it to 1 upon 4 pi epsilon Q over R square. That's the same thing. Now, I just want to point out a simple rule here. I just want to tell you, when you're adding charge, just write a note here, so you guys remember note. Always use the sign, the correct sign for the charge, which means that basically if it's an electron, you got to put a negative sign. If it's a proton, you got to put a positive sign. Is it clear? So automatically your field will be either negative or positive, and depends on that. All right, any questions? So you might have seen that in gravitational potential the force was dependent on product of mass, and in this it is product of charge, and rest is the same, that it's basically inversely proportional to the square of distance, which is the inverse square law. So that makes it easier for us to remember both of them. Anyway, the next thing we're going to do, it is called the electric potential at any point within field. Do you guys remember the gravitational potential definition? Who remembers that? You guys have already forgotten,
Work
right?
done per unit mass.
Okay.
And moving that mass from infinity to the point in a field.
Very good. Now look at this definition. So it is defined as work done per unit charge. This is for the 1 mark, and the second mark is for this charge, work done per unit positive charge, because we need to follow the convention, sorry. And the next mark is for in moving this charge from infinity to a point within field. Easy, right? Do you guys understand now? So both are like pretty simple. Only thing is that between gravitational potential and electric potential, you write work done per unit mass or work done per unit positive charge, right? Now remember, this is the same thing. It is a scalar quantity, and the SI units for this would be joules per coulomb. Joules per coulomb is also the same as volts. So that's the O-level unit. So you should remember this. Okay, please write this down.
What is the second point mean?
Point mean that suppose if this is a charge, right, and it has a field, big field, and there's some point really far away where there is infinite distance from this, right? So if you bring a charge somewhere here, so you need to understand how much work you do per unit that charge, right? Is it clear? So that's potential. Okay. Now, so now this is like in the potential, we should learn the formula. The formula is gravitational potential is written as V, and V is equal to work done per unit charge, as you can see. And if you remember, this is the same formula that we've done in O-levels, right? Work done per unit charge for voltage. Remember?
Yes, sir.
Now I'm gonna derive it into the one we need. So V is equal to F times R. So work done is force times the distance over charge. Force was given by basically K Q over R square times R over Q. Now R and R square is going to cancel out like this, and Q will cancel out. So this will leave us with only KQ over R. Is it clear, everybody? So potential it's kq over r, or v could be 1 upon 4 pi epsilon q over r. Any questions? Now, there are two rules that you need to remember. So please note that number one, charges move from higher potential to a lower potential. That's basically their main thing. And the second thing you guys need to remember is that we can earthing basically means to make zero potential, because earth will always be at 0 volts. Is it clear, everybody? Any questions? Let me know.
Yes.
Okay.
So what does the second point mean again?
Means that earth itself has always 0 potential, which means is that in O levels you might have done this, that there was a charged sphere, right? Let's suppose it was positively charged. Okay, so if you were earthing it, so what would happen? Because this was at 0 volts, negative charges will move towards it. Don't you think so?
Yes.
Because it is 0 volts. And then if this was negative, so you earth it, it means that negative charges would go towards earth. Do you understand? Because
Yes.
yeah, that's fine. Understood? So it means earth is always at 0 potential. That's fine. It's the property of earth itself. Okay. Okay, now small thing that I want to write, and then we'll look at the graphs, because the graphs of electric fields are pretty tricky. So first we're going to look at null point. Null point is basically a point where net electric field strength, because electric field strength is basically a vector, is 0, right? And remember that this is only possible between two like charges, and I'm going to show you how this is possible just in a bit. Okay. Now, before we head on to electric field strength graphs, we should basically go towards electric potential graphs. And from that, we're going to derive electric field strength. And that's the tricky part. Let's try to cover this up today. So first thing is the two like charges, okay? So suppose this is a positive charge. There's another positive charge. So between negative, let's do it simple one first. So from a positive charge, the field goes from positive to negative, as we all know now, like this. This is how the field looks. Sorry for the bad drawing. Please don't be angry at me. Okay. Usually, basically the rule is that the number of lines that come out should go in, so they should be like even, right, between these two. Not an even number, but it should be evenly, distributed. Now, let's look at the curves. So for this one, just for the positive one right here, if this is the potential and this is R, potential in volts, R in meters, so the potential would be the highest in the start, and as it goes away from positive, it would basically decrease. Why do I know this? Because we know that the potential is actually, let me write here, potential is inversely proportional to R, so this is an inverse graph. Is it clear, everybody? So please in 10 minutes rejoin the class. And then for the negative one, I just want to show you that it should look like this. In fact, we are just looking at this direction, so I'm going to put it here. So this is R in meters and this is voltage, but it will be negative. Why negative? Because negative charge will have negative potential. Is it clear, everybody? So as you draw closer to negative, the potential is going to become more and more negative, which means it's going to increase like this. Is it clear, everybody? Because R is like, with respect to R, with respect to negative, the R is reducing. Is it clear?
So I was supposed to draw it upside down?
Yes, because a negative charge would mean negative potential, so you have to put a negative axis. Okay? Now, if you combine these two together, so the net potential graph, net means that the sum of these two should basically look like, so I'm making V net graph in volts and R here. So net potential, it would look like, sorry, I need stroke, wait. And the green one will start from here. Is it clear, everybody? Just like this. Understood? Now, previously we learned that electric field strength is basically the negative potential gradient. Do you remember that?
Yes, sir.
So, if you draw any tangent to find the gradient on this line, whether you draw a tangent here, you draw a tangent here, you draw a tangent here, you would realize that there is none of the tangents will give you a zero value. Do you guys understand this? So basically that means that in this graph, electric field strength is never zero, and that's why you can also see from the drawing itself that the field is distributed. It's not like it can be weak or strong at certain points, but it's never zero. Is it clear?
Yes, sir.
Now, I just want to give you a small, note here, and that is, in case, they give negative on this side and they're positive on this side, and they say, okay, draw the graph, because the field will be reversed like this. So basically, you don't need to worry about it. The only difference that will cause, this will cause on the graph is that now the graph would actually look like this. Do you guys understand? It will be like mirror flipped. Understood?
Sir, can you explain that again?
Yes. Just a second, I need to just text somebody. Okay, so if you look at this, we started from, a positive charge, right, Aman?
It's Nashmiya.
Okay, Nashmiya, sorry. We started from positive charge, so that's why the gradient was positive. I mean, the value was positive, and it ended up, we were going towards negative, so ended up at negative, right? In this one, we started from negative, so it will start from negative, end at positive. You see? like this.
So it's just the opposite.
Yeah, it just flipped horizontally, nothing else. Understood?
Yeah.
So the concept remains the same. You just need to remember that basically, if they flip it, you also need to flip the graph, and it doesn't really make any difference to the values whatsoever. Okay.
The
Yeah.
down part is the red one, or the right side one is the red one?
Sorry, come again.
How did you flip it? Vertically or horizontally?
Horizontally. Like from this. Oh, yeah. This point, I flipped it this way. Horizontal flipping. It was flipped
Okay,
like
so
this.
the one which is down is the red one.
Yeah. Just moved like this.
But the
Clockwise.
negative comes at the top.
Negative part will be at bottom, right? Because this is negative. See, negative charge here first. So you're looking at negative charge. It is showing you a negative value. Positive charge showing you positive value.
Okay.
So basically, starting from this point, you're going here. Do you understand? So first negative, and then so basically the field is becoming more and more positive each time you go towards positive. Is it clear?
So, but the arrows are from positive to negative, right? So why do we go in the other way?
You're not looking at the field, you're looking at the distance from the start to the end. So suppose this was like 0, and then you go towards 1, 2, towards positive. You're not looking at the field, you're looking at the distance. Do you understand? Like in here,
Yes, sir.
we looked from this point, and that's the reason I put the arrow this way, because we're going from here to here, generally not looking at the field direction. Understood?
Yes,
Same
sir.
here to here. Yes, like that. Okay, I hope you guys understand how, because these do get a bit confusing sometimes, but you can always refer to these. Okay, so the next thing is the one where you see a positive charge and a positive charge. If there are two positive charges, then what happens is that the field basically does not connect, it repels. Okay, like that. So most of you have drawn this in O levels, so you guys know that how the field looks. But the thing is that you should also remember that in this sort of field, because it does not connect, you might see that in just the middle part right here, this is the null point, because there is no field here, because it gets repelled. Understood? Right in the middle. That's
so
why
what's the null point in the first diagram?
there's no null point, because
Okay.
it was never repelled, right? And that's why I wrote here that the null point is where net electric field is 0. This is only possible between two like charges, not unlike. Understood?
Okay, sir.
Okay, now let's try to draw the diagrams. Okay, so for the first one, we're going from left to right. Okay, so you don't get confused. So we have positive potential in volts and R. So from left to right, as you go from left to right, the potential is going to decrease. Is it clear? And then if you go from again left to right, I just need to erase this arrow just to show you that we are going left to right. Then as you approach the second positive charge, the potential again is going to increase positively. Is it clear? So the idea behind this is that as you approach a positive charge, as you go closer to positive charge, the positive potential increases. As you go away from it, the positive potential decreases. Do you understand?
Yes, sir.
Okay, I just need to plug in my other laptop. Second. it's working now. Fine. So if you add both of them, so basically you will end up with sort of a diagram. Let me just show you. Okay. Ashmia, okay, we gotta wait 1 minute because this is so important. Till then, can just draw this. Okay, everybody's here. Manya. Okay, so everybody's here. Now, if you combine this, because both of them were positive, so I did not go towards the negative. So you guys need to understand, when you combine both of them, they're going to give you, basically, let me show you what happens really. So the purple one is going to give you a line like this, and the green one is going to give you a line like this. But these are the individual ones that we've already drawn. But the net graph is going to be just like this. Okay, so this is the V net graph you're looking at. Do you guys understand? Okay, by the way, the green and the purple one, you don't need to draw it because they're not required. They basically, why they're like this, because each point, when you add them up, they basically give you the V net. Is it clear, everybody? Okay, now interesting thing is that if you draw a tangent right here, you might realize something very important. The tangent is exactly flat, which means that here the gradient is 0, which means electric field strength at this particular point is 0. Do you guys understand? And that's the point where the null point exists. So this is the null point. Understood? Any questions? Okay, please draw this so that you guys know. So effectively you just need the pink line, okay? You don't need the green and the purple line, but the thing is I just drew it just to show you that basically when you add each point of purple with the green line at each distance, it will give you the pink line. Is it clear? Any questions, please let me know. You guys can hear me, right?
Yes.
Okay, fine. Now, in the third graph, suppose this was like they have given you a negative charge and a negative charge. So the only difference between the negative and negative means that the field is now going into it. but the overall shape of the field is going to be the same. Okay. And the null point will also exist at the same point, which will be somewhere in the middle of these two, depending on, of course, their strength. So there will be a null point here. And when you draw the graphs of these, oh, my bad, they got to be in the inverse axis, like this. So R here and minus V here. So this will give you negative potential reduce, and the other one is going to be like this. So from left to right, R is here, and as you go left to right, the negative potential will then start increasing because you're approaching a negative charge. And when you add these two, now you will get an opposite axis graph. Okay, so here this will be negative V net, words, and we are going from left to right. So the blue one shows you a line like this. The orange one gives you a line like this, and when you add them together, the net will give you basically a shape like this. So again, this is the V net graph that we're looking at, and when you draw, say, a tangent at the center where it is the peak. Okay, this I messed up, sorry. Go back. Okay, so when you draw a tangent here, so basically this tangent is going to be exactly a flat line, so which means here the electric field strength will be 0 because the gradient at this point will be 0. Is it clear, everybody? That's the null point. That's how you figure out where the null point is. Okay, now between the positive and positive, negative, you see both have the same graphs, just they're flipped because of the potential they have. So positives have positive potential, that's why they have positive axes. The negative has negative potential, that's why they have negative axes, right? Any questions? I hope everything is clear, right? Good. Now, why the potential graphs are very important, because without these graphs you can never draw electric field strength graphs, and electric field strength graphs must always be referred back to potential graphs because they have a connection between them, because the gradient of electric field strength graphs, basically the gradient of potential graphs gives you electric field strength, and that's how we can plot the other ones, which we are going to do now in a bit. Okay, should I move on?
Sir,
Yes.
we don't have any values on the axis, right?
No, it will be given in the question, but the shape, I'm basically showing you how the shape actually is drawn. So they may ask you to sketch a graph without values or with values, so you should know how to sketch, right?
Okay.
This is the first class when people have not asked me why are we even doing this. And if you really want to be an electrical engineer or anything related to even aeronautical engineering or something like that, you need to learn these because they play a huge impact on a lot of things. So this has a very practical approach as well. So you need to be very well aware of it. Now, let's go to the electric field strength graphs.
So,
Yes.
now that you mentioned it, where is this thing used?
Basically, when you're designing any airplane, right? So
Okay.
the airplane basically goes through a lot of clouds, right? And do you know that airplane, if they do not, neutralize this and they do not design it in a certain way, it could catch fire because of the friction between its wings and the clouds. So they put a lot of gadgets and stuff which require this to neutralize the effect of the charge's electric field. Do you understand? And then if you become a nuclear scientist or maybe a quantum physicist, then you also need to learn about the electric field strength, because at quantum level, a very small level, gravitational field strength really doesn't matter because the masses are so small, but electric field strength plays a huge difference. And it can actually, the bond formation, the bond breaking and stuff like that, there's so many things that can be done through this. Do you understand? So this is one of the most important things in engineering or medical or even certain parts of itself, theoretical physics, right? So you got to learn this all. Yeah, it's very important. Well, this sort of engineering I've done, it had very less role in it, but I'm happy about it. It's fine.
So how is it related to medical?
Nowadays, they're actually going towards um, basically medical is more and more getting into quantum level, right? Quantum level basically means that you're going through a very small particles that you cannot even see through certain microscopes. Okay.
How would that affect the body?
That's related because the body is made from charge particles which has a lot of charges. That's why. So it is very related to medical as well. Hello. Hello. Yeah, what's up? Huh? Uh-huh. It's a. Mm-hmm. ठीक है. चलो सर. चलो मैं ऐसे कुछ. I'll ask. उसका आना था. Of course. Okay, bye. Acha, so now let's look at the electric field strength graphs. Okay, so for the very first one, I don't want to draw this again, so I'm gonna just copy this. And then I'm gonna show you how for the first one it is drawn. And you just need to follow what I'm doing right now, because electric field strength is a vector, and vector follows the direction of the field itself, right? So we're also going to look at the direction of the field now, not before, because that was scalar, right? So when you draw the graph of this, you don't need any special oh my god, wait, I need to do it again. It goes like this and then it goes like this. Messed up again. Okay, never mind. So this is electric field strength in Newton per coulombs. This is also electric field strength in newtons per coulomb, and this is R in meters. Now let's look at it. If you look at the graph of this, as the potential graph of this, right here, you might see that basically the gradient here was maximum, right, and negative. Do you agree? Do you know the graph rules? Everybody is
So which point are you talking about?
the one I drew.
Okay.
This one. If I make a tangent here, this tangent is basically, it has a gradient like this, right? Understood? Do you understand this?
Yes, sir.
So this means the gradient here is maximum, right? If the gradient here is maximum, that would actually mean that the electric field strength in the very start is also going to give you a maximum value. Do you understand? But as you go through the graph, you see that at this point the gradient is minimum, because then it starts to increase in the opposite direction. Agreed? You see, it gets again the same way. So basically the line, the tangent gets flatter, and then the tangent increases. Everybody can see that? Or should I draw this side by side? I think I should draw this side by side. You guys will be confused then. Because, wait, let me copy this too. Okay. This is the most tricky part here. Okay. Now check this out. In the very start, in the beginning, here the tangent is maximum, right? It's completely vertical, so the electric field strength here is maximum. If you draw a tangent right here, it is the minimum at this point, and then the tangent increases again, the slope increases till here. Do you guys understand this? You see? Look at the tangent only. It means that at the very center, the tangent basically has the minimum value, and at the end the tangent has the maximum value again. So basically it would actually reduce the field strength in the middle, and then the field strength will increase again like this. Do you guys understand this? So basically the gradient of this graph basically is shown right in this graph. Any questions? You guys got it, right? Okay. Now, let's check out the next one. Let's check out this one.
No, but this class end.
Huh? This class will end probably when we're done. You have another class after this?
No, but I have to go out.
You have to go out? Can you wait 10 minutes more?
Yeah, that's fine.
Okay. Now, so for this one, first of all, I'm just gonna draw the potential graph. I just okay, I'll copy this, and then because I need to go faster, graph has to leave. So putting it here. So for this one, let's put it right here. And oh my god, the software is like glitching all the time. I don't know when they will fix it. go here. Thank God. Paste again. Anyway, so now look at this. I'm just erasing the extra graphs because we don't need this. We just need the VNet. Now, in this sort of graph, you see that we're gonna make electric field strength Newton per Coulomb, electric field strength Newton per Coulomb, R in meters. Now check this out. The gradient here was this way, alright, and then at this point the gradient was 0, and at this point the gradient was in the opposite direction. Like this line, if you take it as positive, this line is negative. Do you guys understand? Or something like that. So if you draw this, it means initially the gradient was like maximum, and then it would reduce to 0 where this point is, this point, and then it would increase in the negative direction because it is gone in the negative direction, increasing. Is it clear, everybody? Please let me know if you understand this.
Yes, sir.
Now, for the other one, you can actually guess again. You can just guess, because for this one, it will be I just need to copy the graph as well. Side by side you can see. Oh crap. So when you draw the graph for this one, you can actually guess, but basically it will be like flipped again, because just the values here, Newton per Coulomb, Newton per Coulomb. Now is all the extra things. Now here the gradient was maximum, then the gradient was 0, maximum 0, and then maximum in the opposite direction. So that would mean the graph would start from here, go 0, and then increase in the other direction. So between those two graphs, the only thing is they will be like flipped, otherwise it's the same graph. And that basically, with the electric field strength is 0, this is the null point. Everybody understand this? Any questions, please let me know. Okay, so I just want you to do one example, just one example. Rafi, I have just asked 10 minutes, it's only 4 minutes up till now. So one example, and then we're good to go. Okay? Basically, that's a question that I want you to do, because if you don't do it, I won't basically consider that you understood this. Okay. I am trying to post it. Wait. Sync. Please sync. Crap. Okay, never mind. It's not syncing. So I have to make it again. Okay, I'll just have to draw it. Okay, so in one of the questions they have given, suppose the example, they say they have given you two graphs. So yeah. Okay, so they say this is a VNet graph, this is R, and they want you to draw electric field strength graph. So they say draw the electric field strength graph. Okay, looking at this, I also put some guidelines so that you guys can see what we can actually do. Okay, now you need to just sketch it. Okay, remember that electric field strength is basically negative potential gradient. You just need to remember that. Okay. Okay, hurry up, please. Okay, you guys are done?
Yes, sir.
Alright, now let's see this. So for the very first part, please compare your graph here. This line has a positive and constant gradient, right? So it means that we need to make the negative. The gradient is basically this part is positive, but negative time makes it like negative and constant. Do you guys understand this? Now, this section. Yes, you see this line has a positive and constant gradient. If you find the gradient, it will be positive and constant, right?
Yes, sir.
But the electric field strength is negative potential gradient, which means the positive gradient value on V net will be the negative electric field strength value. Do you understand?
Okay, sir, got it.
Then this line has no gradient, so the gradient here is 0, which means the line will shift here, it will be 0 till this point. Then this is nothing. This one is 0 again, so it will continue to be 0 because it's a flat line. This line is 0 again, so it will also continue to be 0. And then let me draw it with a different color because then it will be more visible. Okay. Now for this one, again it has a positive and constant gradient till this point, which means that positive and constant would mean that it would be negative value of electric field strength and constant, like this. Now in this section you might see that basically here the gradient is reducing and it is basically a negative gradient, negative and decreasing gradient. So negative and decreasing means electric field strength will be positive and it will be decreasing, so it will go up and now it will be decreasing. Do you guys understand this? So your graph should look like this.
So there will be a constant decrease because the graph has the curve in it, right?
Yes, but the thing is you can never tell unless you have values. So if they say sketch it, you just draw a constant, like constant decrease.
Okay.
Alright. Okay. Any questions now? Aman, everything is clear. Abdul Mois and Fatma,
Yes.
Okay, great. So I'm sorry for the long class, but it was very important that I had to complete this.